Now I'm going to be doing a demonstration of the very famous box problem. So what you're considering here is that you have a piece of cardboard that's a rectangle, 20 inches by 32 inches. And what we're going to do with that piece of cardboard is cut away 4 square corners from the cardboard rectangle and fold the sides up so it forms a box with a base and its 4 sides. And the question is, from this 20 inch by 32 inch cardboard rectangle, what should the dimensions of that cardboard box be in order to maximize the volume? So here's what we're considering. We're considering that we're going to be cutting away 4 equally sized squares from the rectangle. And they have to be the same because they're going to be forming the height of the box on all 4 sides. So that x would be the height of the box once the 4 corners are folded up. But what about the length and width of the base? What we're looking at here is this inner rectangle. Once the square corners are cut away, will end up forming our length and our width. So we would have the length here, and you would have the width here. The length and the width. So what would that length and width be? The height of the box, of course, once we have cut away the square corners and folded it up, the height would be x. And then the length, if we consider the length to be the long side, the entire length of the cardboard piece was 32 inches. But if we remove x twice, then that length is going to be 32 minus 2x. The width, similarly, had an original length of 20 inches, but if we're going to cut away a length of x twice from both corners, the inner width that we're going to be left with is going to be 20 minus 2x. And therefore, the volume of the box is going to be length times width times height. Length, width, height. So if we write that down as the volume of the box in terms of x, the volume in terms of x is going to be x times 32 minus 2x times 20 minus 2x. The height of the box, the length of the box, the width of the box. And therefore, multiplying all of that through, we're going to have the volume is going to be 640x minus 104x squared plus 4x to the third. That would be the volume in terms of the x, because of course the length and the width depend on the length of x, the side of the square that we're going to be cutting away from the corners. So in order to maximize the volume, of course, we're going to take the derivative. The derivative would be 640 minus 208x plus 12x squared. And in order to maximize, we're going to set that equal to 0. So since we're setting it equal to 0, we could actually simplify by dividing that entire derivative equal to 0. A common factor of 4, just to make things a little bit easier, would lead to the fact that this would be 160 minus 52x plus 3x squared set equal to 0. So factoring that, we could factor that into 40 minus 3x, 4 minus x, set equal to 0. Therefore, x being set equal to 0 could either equal 4 or x could equal 40 divided by 3. However, we know that 40 divided by 3 is not going to be a valid answer because that's approximately 13, a little over 13 1/3. We would not have room to cut away 13 1/3 for both corners because twice that would exceed the 20 inches. So we know that this answer itself is not going to be a valid answer. So therefore, the valid answer we want to use is x equal to 4. Now, before we go on, how do we know that that actually maximizes the volume? It doesn't minimize the volume. Remember, we could always check the second derivative. So if we take the second derivative of the volume, the second derivative would be then the derivative of the derivative, which would be negative 208 plus, that would be 24x. And then if we take the second derivative evaluated at 4, we get 208 plus 4 times 24 is 96. We see that this is actually negative, and a negative second derivative indicates that yes, we do have a minimum, or we do have a maximum. So that would be the height of the box maximized. And then what would be the length? Well, you could go to the length, 32 minus 2 times 4 would give you 24. For the width, you would get 20 minus 2 times 4. That would give you 12. And then the maximum volume, you would multiply the length, width, and height together. So therefore, here's what we have for our final answer. Our final answer, the length of the box would be 24 inches, the width would be 12 inches, and the height is 4 inches. And then multiplying length times width times height, we have a maximum possible volume of 1,152 cubic inches. And remember to always label your final answer.